Okay, let's get started. So today we're going to continue our discussion of MRI. Before I get started, are there any questions about course material or course logistics, projects, anything? Okay, go ahead. Yeah. Yeah, that's a good question. So obviously, I've been trying to give a lot of thought to what to do for homeworks, given the situation. So what I've decided to do is I'm going to have one more homework assignment. That's not going to be due next Friday, but the last Friday of class. So it is close to the project, I understand, but you have 2 weeks to do it. So you can sort of organize your time however you want. I don't want to have people working on, if you're going away for Thanksgiving, it's sort of a bummer if you have to, get it done by Friday night. So this gives you some flexibility. Now, this is going to be sort of an experiment. So I'm going to try to make most of the homeworks. I'm started working on it already. So the homeworks probably will not be come out, and I'll make an announcement about this on Canvas, but it's going to be MATLAB graded, automatic graded homeworks. So you'll have the chance to write some MATLAB code, and MATLAB will automatically grade it for you. So MATLAB has this thing where you can sort of submit your answers and it'll just keep telling you. And so I think that actually might be better for learning. You can just keep working on it till you get it right and you get the immediate feedback. Okay. So what it's gonna do is help you design gradients, RF pulses. They'll be fairly short, so the amount of code you have to write for each is not going to be very much. It's not maybe 10 or 20 lines, something like that. So you're not looking at a big project, but it will cover enough principles such that it'll give you a taste for example, some of the stuff we're going to talk about today is really we're talking about how do you do design, right? And so there'll be some very simple design problems, like given these constraints, write a function that will design such and such a gradient pulse for you. So it is an experiment. This is the first time I've done it, so there might be some glitches. So what I will start doing is over the next few days, start issuing problems and publishing them as they become available. What I would like to ask from the class is if you could start at least trying them out and give me feedback. So if there is a problem, I can fix it. If you all wait till the last minute to do it, then obviously, it's gonna be harder for me to fix issues. I mean, I will test them out beforehand, but there's nothing like having some students you don't have to submit it, just try it and see if you have any issues with it. And so hopefully together we can sort of debug that. Let me see. I think that's about it. I mean, I think that's so in terms of when homework, I think homework 4 is partially graded. Homework 5 and 6, we're going to wait on to see what happens in terms of whether the TAs will come back and grade that, or whether I'll just do a fairly light grading towards the end of the course. But I think the good thing is that the homework assignments for the last homework are sort of independent of the previous homeworks. They're really mostly based on the lecture-based material, and it's a totally new design anyway. So this is going to be an experiment for all of us. I think that answers your question, sort of. Okay, and probably more than you wanted to know, but I'll send an announcement about that. Because of the way things are designed, it's going to look a little different on Canvas. It's going to be like there's going to be like a homework 7 group, and then there'll be like different little sub assignments under that, because I haven't figured out. It seems like in Canvas it's like one MATLAB problem per assignment, and then that gets graded, and then so you'll see it'll be a little different experience for you, but hopefully it'll be different at least. Okay. Yes, question.
For the second project, is it like the same procedure if you want to, like, you have to come up with a topic for your group and email the TAs to get approval for it?
Yeah, actually, so as it says, basically you can email Jonathan, but also email me. So people have already started doing that, and if you look on the Google Sheet, already two projects have been approved. If you have a green box by your group, then your project has been approved. So you don't have to wait till next Wednesday. You want to, and also if there's a project you really want, it's first come, first serve. So if you've already submitted a project, I've said yes, make sure you enter your thing on the Google Sheets and put a green thing. And then once I look at it and I verify that, you were one of the first to do it, I will typically limit any subject to about 2 groups. Okay, so for example, There's one group that already has claimed compressed sensing, so there's room for one other group to do that. I mean, if you have a very compelling argument, I might expand it to 3 groups, but I don't want to have 10 talks on the same thing. It actually also helps you in terms of, if you do pick something that other people do, then there's more likely a comparison of, hey, this group did really a lot. And then, so it does tend to hurt the grading if 5 groups do the same thing, then it's much more easy for us to sort of see which did a better job. So actually picking more diverse groups gives you a better chance of distinguishing yourself. So I would encourage you to talk to me. You can also send me emails. I had one group, there's some back and forth where they send an idea. I said, well, look, maybe do this, do that. And so you don't want to wait to the last minute necessarily to do that. Okay. Any other questions? Okay, so let's start the lecture material for today. So we're going to continue our discussion of sampling, aliasing, and resolution, and hopefully start a little bit about returning to RF excitation and discussing something called slice flexion, which is a very important part of MRI. So just to remind you, the MR signal is sort of what we're measuring is, as the signal is coming as a function of time. At every point in time, we are getting a point in the Fourier transform, okay, a point in K space. Okay, so that was one of the questions, and most people got that, but I think just want to emphasize that if I look at any point in time from an MR signal, that corresponds to one place in K space. So one value of Kx, Ky. So one question is, what spatial location does that refer to? So if I have a point Kx and Ky, where in the object am I looking? Does that correspond to any particular spatial location in the object? No, it's the whole object, right? So that's something to consider, that just like in CT, every time we get a projection, that's a projection over the whole object. In MRI, it's really a projection of our object onto a Fourier function, and that's what we're measuring. Okay, so it's always the projection of the entire object onto what's called a Fourier basis function, and that's what we're measuring at each point in time. So for example, if our object was this 2-dimensional rect, then the MR signal as a function of Kx and Ky, we expect to get a 2-dimensional sync. Okay. And then the thing about MR is just how do we collect this data? Okay. And what we discussed last time is the most simple way you can think of is just do Cartesian, right? We're going to acquire one line, maybe we acquire this line first. So we go through in a time, okay? And then on the next repetition, maybe we acquire this line, okay? And then maybe we acquire this line, okay? So similar to in CT where we did different projections, in this case, we're just acquiring different lines of K-space, okay? And then here at the center, we're going to acquire this big data, all right? So as a function of time, there's time going this way is actually pretty fast. We can just zoom across it, okay? And remember, this is called the frequency encode. Frequency, or also readout direction, okay? And then for spin warp, this direction here is called phase encode. Okay, and that's where we sort of step line by line by line, and that tends to be the slower direction. Okay, so there's typically a fast direction where we just zoom across, and there's a slower direction where we sort of step by step. Okay, so just by convention, this is Kx and this is Ky. That's just the convention we have in MRI. Okay. Now there could be in 3D imaging, you could also add the case of Z, and so you could do phase encoding in Z as well. Okay. Now we don't actually have to. I mean, there are trajectories where we don't want to do this stepping, and so the other thing we could imagine doing is we can acquire the data, like we could start at the center and just spiral out and collect the data like that. So we could imagine collecting the data like this. Okay. So we just go very quickly. So there's lots of ways to go through K-space. We're just going to go through the most basic one. And one of the MATLAB problems online may or may not have that, but I'm sort of still working on that. So what we talked about last time was sampling, and just to remind you, your design problems are going to be, you're going to be given like an FOV, field of view, and maybe some resolution. And one of the first things you have to figure out is what's the delta kx and delta ky, and what's the wkx and wky. Okay, and then basically, so that's the first step in any MATLAB code you're going to write. Given some inputs, figure out what those things are. Okay, and then the next step is relate those to the gradients. And we'll go through some examples of that today, but that's your MATLAB code essentially is going to have like 2 steps in it. Okay, so you might have 1 or 2 lines figuring out the delta k's, the w's, and you have a couple more lines figuring out the gradient, amplitude, and duration. All right, that's the design problem. Okay, just to remind you why sampling matters in k-space. If we don't sample finely enough, then we get these image overlaps. Okay. And so the first Nyquist condition we have, or the Nyquist condition is basically to avoid the aliasing. And so your design equations are simply these, and then in your code, you can always just say delta kx equals 1 over field of view of x, delta ky equals 1 over field of view of y. All right. And you know, if sometimes you might be only asked to design the x gradient, for example, in a problem, in which case all you care about is the field of view in x. You don't actually care about field of view in y. But if you're asked to design both, then you need to take both into account. Right? Okay, so this is similar to one of the things in the pre-lecture quiz, but let's do it anyways, just simply because it's good to review, I think. So let me start the poll on this as well. Let's see, multiple choice. Okay. So the polls launch on Zoom, and then in class we'll do an audio poll. So here's the question. You're given this object, cosine 2 pi 3x plus 2y, rect x3, rect x4, rect y over 4. So you're asked to figure out what's the delta kx and delta ky required to avoid aliasing. All right, so go ahead and take a minute to think about this, and then we'll reconvene in about a minute. Okay, so I think the poll is pretty much done online. So let's go ahead and also look at it in person. So at the count of 3, just yell out what you think is the right answer. 1, 2, 3. Okay, sort of B, C, sort of not a strong thing. Online is much stronger. 82% went for C, so they're much more confident or awake. I don't know, either one. So let's look at that. This is an object that has a width of 3 here and a width of 4 here, right? Okay, so that's the extent of the object. And then inside, it's got some like, you know, some sort of cosine pattern in it, right? But does that cosine pattern matter for this problem? No, right? Because it doesn't affect the field of view. So whatever's in here, I could just draw like anything in here. It doesn't really matter because it's the aliasing just depends on what's the extent of my object. Okay, so this here is meant to sort of try to mislead you in terms of thinking, oh, you need to worry about that. Actually, the only thing you need to worry about is this. Okay, and so we know that the field of view of x is 3 and the field of view of y is 4, right? So therefore, this must be the correct answer. Okay. So I think most of you got that right on the pre-lecture quiz. A few people just sort of swapped the order of the x and y, so just check that. The good thing is when you do the MATLAB automatic grading problems, you know, you can sort of do multiple attempts and at least debug your problem like that. Okay. Okay, so that's basically all, and we'll revisit the design problem in a minute in terms of applying this to actual pulse sequences. But the next thing we need to talk about is windowing the data. And this is the idea that, you know, the Fourier transform is defined from -infinity to infinity, right? But obviously we don't want to do that, right? We want to be within some regime. So what we're going to do is, if this is the Fourier transform, which should go from minus infinity to infinity, we want to use a windowing function to say, I'm just going to look at the Fourier transform within some narrow window. All right. And I'll just close this here. So this is multiplication in the Fourier domain, right? And therefore, I'm going to convolve my object in the image domain. So the process of windowing in one domain really results in convolution with some function in the other domain. So the most common example, what we'll use for this class exclusively, I mean, obviously there can be projects looking at other different types of windowing, but this is what we'll use just to keep things simple. So all I'm saying is in Kx and Ky, I'm going to just limit myself to Wkx, Wky. Okay. Now remember, we actually don't actually multiply by this window, right? It's just we don't collect the data outside the window, right? So this is mathematically saying just don't collect the data outside this window. It's not like you collect a lot of data and then you window it, although you could do that. And that, you could always do that post-processing and try different blurring. But in general, for the design problem, for designing your acquisition, this is just a way of saying, okay, if I only collect data within this window, what's the effect on my image? So the effect on my image is I have to convolve my image with the inverse transform of this. So that's just going to be a sinc, two sinc functions. Okay. And so these are going to look like, for example, in the x direction, it means I'm going to convolve with a sinc in x, right, which has its first zero at 1 over wkx. All right, so that's basically the sinc function. So you can already see that what's going to happen as I make this wkx bigger, this 1 over wkx is going to get smaller, right? So the farther out I go, the narrower that sinc function becomes. And so when I blur with that sinc function, it doesn't affect me too much. On the other hand, if I really close my wkx and make it only acquire a little bit of data, then that 1 over wkx gets big and that sinc function gets big. And that's basically going to blur my image a lot. Right? So this relates to resolution. Okay, the resolution is sort of, how blurry is your image? If you have a low resolution image, then that's pretty blurry. If you have a high resolution, image, or one of these like super duper HD TV, whatever, with super duper resolution, then you can sort of see things in much more detail. So the bottom line is we're going to convolve our object with these sinc functions. So as we talked about last time, the nice thing is that the effective width of a sinc function that has a 0 at wkx is just wkx. Okay, so that 1 over wkx. So 1 over wkx is a good sort of measure of how fat that blurring kernel is. Okay, so what we say is the resolution for this class, our resolution is delta x, and that's equal to 1 over delta kx. Okay, and similarly, delta y would be 1 over wk sub y. So where this comes in is, say your technician or your doctor says, I want to acquire a resolution with some image, some resolution, like a millimeter, a centimeter. You're like, fine, your MATLAB code or whatever code you have would just say, okay, from that, if I know delta x, I can always solve for wkx, right? So that's one of the other simple design equations that you'll have in your MATLAB code. So let's look at an example of sort of why that makes sense. So imagine I had a window of wkx, right? So let's say I acquired some data wkx. So that's the full window from minus to plus, right? That means the highest frequency component I'm going to acquire here has a frequency of wkx over 2, right? Okay. So that means the period of this is 2 over wkx, right? So that's something with a period of 2 wkx goes up and down. And you can sort of see this function here that goes up and down, it could represent something that's sort of changing up, down, right? And so the effective width of so this width is 1 of wkx, it sort of makes sense that that's sort of the resolution, right? Because something with this frequency could represent something that's changing at that rate. All right, so that's one way to look at it. The other way to look at it is, let's consider what happens if we had two delta functions spaced one apart. Okay, so this spacing here is 1. Okay, so if delta kx equals 1, then that means our resolution is equal to 1, right? And in that case, each Dirac delta function gets blurred. So this is a blurred version of 1, and the green is a blurred version of the other. And the sum of those two is just this sort of red thing. Okay. So we're right at the limit. At our design equation, we're right at the limit where actually you cannot differentiate those 2 points. Okay. Now let's say we go to a higher WKX. So now delta x equals 1 over 1.5, which is equals to 2/3. Okay, now you can sort of see those sinc functions, it's here in green, blue and green, are narrower. So when I take the sum of those 2 objects, now there's a little dip there. So you could, if the image was not too noisy, you would be able to distinguish those 2 dots from each other. All right. Now we go to WKX equals 2. So now the resolution is 1/2. And now it's pretty clear you can distinguish those 2 dots from each other. Okay, because the sum of the images is just goes up and down, up and down. And even here, if there was a lot of noise, you would still have a good chance of figuring out that there's 2 dots. Okay, so design equations, we're really at this limit. We're just saying this is the minimum you need. Once you go WKX beyond that, then you start getting into this regime where you can start differentiating things. All right. So for the class, you can always be at sort of this limit where the resolution is sort of at this limit. Okay. Any other questions? Yes.
So I noticed in the W equals 2, where delta x is half.
Yes.
Regime, we have the zeros for the same function are kind of like aligned up. So you have orthogonal functions. Is that just like, is that like the limit where you get to distinguish the 2 spread functions?
No, you can still distinguish them here, even in the middle, right? It's just, if you had no noise, then you can still distinguish that. So it really becomes the interaction between how much noise there is and like, if there's a lot of noise, then it'd be hard to detect this little dip, right? And it'd be still easy to detect this dip because this dip is big, right?
Yeah.
But you can still detect it here.
Okay.
Yeah, you can still detect that there's 2 little things there, right?
So the window size that you would be kind of determined is also kind of linked to like how much noise you'll have in the machine. Yes,
and I'm not sure how much. Yeah, I don't know how much we'll build into the noise, but it's actually a sort of thing where basically the other thing is the more data you collect, that's also reduces your noise as well. So actually going out collecting more data actually gets you better resolution, also reduces your noise. I think we'll probably look at that from a linear algebraic point of view. So there'll be something on that. But what's the cost of collecting more data?
Takes more time.
Yeah, more time. Okay. So the 2 drawbacks of more time is time equals money, right? And so, the standard has gone from, it used to be people were happy to have like an MR exam, like an hour per patient, right? Now, like the administrator's like, we want it done in 15 minutes, right? Because it's like ka-ching, 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 right? We paid $3 million for this MRI machine. We want more scans done per hour, right? So that's one thing, okay? So there's just the economics of people trying to, survive. Especially, this is a fairly competitive, San Diego is a fairly competitive environment. We've got UCSD, we've got Scripps, we've got Sharp, we've got Kaiser, there's independent medical imaging centers, UCSD actually has quite a hard time because, we try to like sort of say that we have higher quality, but, in terms of whether people are willing to pay for that is another matter. Okay. And whether your insurance is willing to pay for it is also another matter. Okay. The other thing that we've talked about is, patient, what can the patient withstand? Right? Like if someone is really sick, they're not really going to be able to stand a 1-hour exam where you're doing this and this and this and this, right? Or let's say you're imaging a child or an infant. you may have 10 minutes where they're going to be still, right? And you don't want to have to sedate them, right? Now, obviously, if it's very serious, you will sedate them and anesthetize the child, but you would rather not, because even anesthesia is a risk. So there's always this, so a lot of the rapid imaging, like compressed sensing, a lot of the impetus for that came out of like pediatric radiologists. We're saying, hey, anything we can do to speed up the imaging time is good, because if you scan a child for 5 minutes, but they're moving for half the time, your image looks horrible. Okay, so some people looked at motion artifacts in CT, you get similar issues. I mean, there's also motion artifacts in MRI, which I don't think it listed as a project, but that's certainly a good project, motion artifacts in MRI. So, yes.
A question for the differentiation between the blue and the blue.
Yes.
Would that just be like things that you would X-ray or
Yeah, so actually you don't actually get to see the green and the blue. All you see is the red, right? The red is the sum of the green and blue. And this is also ideal. This is like sync functions. So the idea would be, let's say you had two little nodules, like of cancer or some like little tumors, right? And you wanted to see, is that one tumor or two tumors or something like that. Okay. So just any time where you're trying to differentiate things, like, so 2 dots is just a simple example, but resolution matters if you're trying to like measure, is something growing, or just how accurately can you measure size. Okay. So basically, to sum up everything up, we have our Fourier transform, the ideal one, and we're going to sample it. So this is the sampling, and we're also going to window it. Okay. And so this is all multiplication in the Fourier domain. So this means convolution in the object domain. So we're convolve with this cone function. So this is the replication, right? So we repeat our images, and then this part is the blurring. Okay, so this relates to aliasing, and this relates to resolution. Okay, this part is related to FOVX, FOVY, and this part's related to your resolution delta X and delta Y. Okay, and these parts are going to tell you your delta KX and your delta KY. And these parts are going to determine your WKX and your WKY. All right, so that's how it all fits together. Okay, so let's take a look at that. So let's say this is my object. It's just a very plain old vanilla rect function, and it's got this Fourier transform, sync function. Okay. Now, first thing is I'm sampling that sync function, right? And then I'm also going to window it. So I'm not going to collect the whole sync function. So I'll end up just with it within some square here. I end up with samples of my sync function. Okay. So this is all multiplication in this domain. So that means I convolve with the inverse transform of this guy, which looks like this. Okay. And so that's going to replicate my images. And I also convolve with this sync function, which is going to blur each of those replicas. So each of these, if we zoom in on it, is a slightly blurred version of my original image. Okay. So those are the two effects that we're trying to design for. So these are basically the design equations we come up with, which is, we want to determine delta KX, delta KY, and WKX and WKY. And sometimes you might see terms like KX max minus KX max. That just indicates the maximum K space we went to. And if we're symmetric, then WKX, which is equal, for example, 2 times KX max. And then these have inequalities, but in any design problem you have, you can just set these to equal. All right. And you'll see that. Okay, so let's do another poll together. Let me launch this. How do I relaunch this? Relaunch the poll, relaunch. Okay, so here is the same object we had before. But now, instead of asking you what's the delta KX, delta KY, you're asked to figure out what are the KX max and KY max parameters needed to achieve this resolution. So go ahead and takes a little maybe more thought than the other one, but give it about a minute or two and sort of see what you think. Okay, let's take a look at this, and or take another 30 seconds and just sort of if you're online, just enter in your best guess. Some people haven't responded yet. Okay, so in class, at the count of 3, just say as loudly as possible your favorite answer. So 1, 2, 3. Okay, so I think fairly tentative responses, but I think C was what I heard. And C is also the little winner online with 63%, followed by B and E with both with 21%. So let's see which one makes the most sense. Okay. So does this matter at all, the rect x of 3, rect y of 4?
No.
No, right? That's the field of view. We already dealt with that. Okay, that determines our delta kx, delta ky, right? So we can ignore that. So now we just have to focus on this, right? This has the form cosine 2 pi kx x plus kyy, right? So what's kx equal to? And what's ky equal to? So just based on that, what do you think the right answer should be? Yeah, which one of these looks like the other? Okay. All right, so if you just had to take a wild guess, you had like 10 seconds to pick an answer, that would be your best option, right? Because everything else looks slightly different, right? And that is the right answer, but let's look at why that's the right answer. Let's, for example, just look at something. Kx equals 3, whoops, I'll do that. This means the period is 1/3, right? Okay, so that means if I drew a cosine or sine, you know, this would have a period of 1/3. And so half a period is 1/6, right? So it would make sense that our x resolution is 1/6, right? And so WKX should equal 6, right? But then kx max, if things are symmetric, is just wkx over 2 equals 3. Okay. And by the similar argument, you could say ky max is equal to 2. Okay. So that's one way to look at it, if you want to go through all the equations we did. The other thing you can do is say, well, if my object has something varying like this, right, I better have a Fourier function that goes up to that frequency so I can match it, right? Because Fourier transform is essentially saying, what in my object is a good match for my Fourier function? So if I have something varying like that, I need something at that frequency to match it. Okay. So if I know my frequencies go up to 3 and 2, I better have something. And then the maximum I would need is 3 and 2, right? Something at those frequencies. All right. So that's essentially, so basically, you know, in the real world, like how do you decide on delta x and delta y, right? That's always a good question. Like, you know, how do you know whether you need a millimeter or a centimeter, you know, half a millimeter, 10 microns? The answer is it depends, okay? Because if you have all the time in the world and you really, really want to see something in detail, and let's say you can take the brain out of someone's head and scan it for 24 hours, then you can say, I want a resolution of like 100 microns, right? But if you're in an emergency situation or you want to go really fast through someone's brain, then you might be okay with 3 millimeters, because you're like, you know, if I have to go to 1 millimeter, it's going to take too long, the image won't look as good. And so it's just always a trade-off, okay? And quite frankly, when we're making these decisions for research, we just sort of take our best guess usually. Like, okay, this is what people do, we think we can do this, and then you iterate. So, you know, for those of you who haven't done research or worked in the real world, you know, a lot of decisions are just based on your best guess, like, and then you iterate, and you sort of say, okay, well, that was not enough, or that was too much, or that's good enough. Okay. You know, there are no answers in the back of the book in the real world. So you just got to make it up as you go along. All right. Okay. Let me just close this so it's not showing here. So I don't think anything on chat. All right. Okay. So this is a view from a GE scanner of what a console looks like. So when you if you're a technician or radiologist or even a grad student or a postdoc, and you're at the console, this is what you would see if you're on a GE scanner. Siemens or Philips, they all have their own thing. But I wanted to point out a few things that we're going to look at here. So you'll notice here, there is a field of view. So that's FOV. This is saying I want a 24, in this case, it's 24 centimeters. Okay. Slice thickness, hopefully we'll get to later in this class, it's saying I want a 5 millimeter slice thickness. Now, how do I know this is centimeters and millimeters? It's just, you just have to know. You know, that's just part of the training. You know, every console will have its assumptions, and as part of the training, you just know what those things are. Okay. And now you'll notice in this one, this is defined as F field of view of X, just by convention. And you notice there's no field of view Y here. And that's because in GE, for whatever reason, they've called the phase field of view as a fraction of the FOV of X. So in this case, FOV of Y equals this phase field of view times FOV of X. Okay. So in that case, if it's 1, then the field of view are the same. Okay. If it's 0.75, then the field of view in Y would be 0.75 the field of view in X. So that's, you don't need to know this. I'm just explaining, you know, how one example of how this works in the real world. You also notice there's no resolution here. There's no delta X or delta Y here, right? But what there is you see this frequency and phase. Okay. So this is going to give me my delta X. This is going to give me my delta Y. Okay. So in this case, delta X is going to be the field of view in the X direction divided by 256. Okay. So basically how big my object is and how many pixels or voxels I have. So this is going to give me, and notice that's, I know it's delta X because remember this is the frequency direction, so by convention, and phase is always the Y direction. And so in this case, I know delta Y is equal to a field of view of Y over 128. equals field of view of x over 128, because field of view of x and y are the same. Okay. So just given those two things, which is going to be a bit bigger? Do I have to go out farther in kx, or do I have to go farther out in ky? Where do I have to spend more time? Along with kx or ky? Go ahead. Someone say something. Kx, right? Because the resolution is smaller, right? The delta x is smaller, so I want finer, better resolution. So I've got to go farther out in k space to get that. What about delta kx, delta ky? Are they the same? Are they different? In this case, that's my sampling in kx and ky. Do I have to sample more finely in kx than ky, or do I sample the same? Any ideas? Same. Okay, why would they be the same? Yeah, the FOVs are the same, right? So we can say delta kx equals delta ky equals 1 over field of view of x. Okay. All right. Any questions on that? All right. So let's go and sort of design our first pulse sequence here. So we're going to look at a spin warp pulse sequence. Remember, spin warp, we go line by line by line by line. And we are going to have an RF pulse. We assume we're at the center of K space at every RF pulse. And then we have both a readout gradient and a phase encode gradient. And we just repeat this process over and over again. Notice the readout gradient stays the same. We're always just zooming across K space. And then the phase encode gradient varies, okay? And so what's not shown here is those initial gradients are doing this for us, right? They're taking us like that. They're going from the center of K space out to that, okay? So that's the initial trajectory that we're taking. Oh, sorry, this goes the other way. All right, so that's what these are called dephasers. They basically take you out to some point K space, and then this is really where the readout occurs, and that just zooms across K space. So what does things look like in K space? So basically now we're just repeating that, and we're sort of showing where you are in Kx as a function of time, and sort of see we go out to some negative value of Kx, and then we linearly increase and cross Kx with the rest of the amount of time. Okay. And then in Ky, we go out to some location in Ky, and we just hold that value. And here we hold the value, and we go another value, and we just hold those values. So that's in time what's happening. Okay. So what actually happens in the MRI machine? This is a very simplified version of what sort of happens. This actually isn't what people do, but this gives you the idea of what's going to go on. So remember, our signal is at the Larmor frequency, omega naught equals gamma b naught, right? So we've got this thing, our RF signal is at this high frequency, okay? So one thing is, just from the point of, but it's a fairly narrow bandwidth around that, right? So for those, especially for you, those of you who are double E's, you don't want to have all your electronics work at this very high frequency, right? So you want to mix it down to baseband, right, low frequencies, and then do the electronics there. Okay. Now, typically, we don't mix all the way down to baseband immediately. There'll probably be intermediate mixing where we might mix it down to like 10 megahertz first, okay, and then mix it down. So there's typically analog mixing down. So typically, most modern things will go from omega naught to some intermediate frequency omega m, and then down to DC. Okay, so the mixing is typically done in 2 stages, and the reason for that is this is all analog, and this is digital. Typically, that's how it's still done. Now, as digital gets better, this is going to take over. Like if you could actually sample, there are people who are trying to actually sample the waveform at that 127 megahertz or whatever. Or if you're doing low field MRI, if you're actually doing portable MRI, then you can just do everything digitally. Okay. And the advantage of things doing digitally is everything is just math. It's just very precise, right? In analog, as anyone has done analog design or circuit design, things depend on temperature, there's just all these effects, right? I mean, we just had something where one of our scanners, the temperature in the room, it went up by like 3 degrees centigrade this week, and it just changed the performance of the system. So things are just like fine, like however they design the system, they design it so it only works within a small temperature range. And once we go out to have that range, we have to like worry about the room temperature. Okay. So it's sort of a pain in the butt, but that's the way it is. But this simple picture is sort of useful. Essentially, we're going to multiply by a cosine and a sine term, right? And that's because, remember, the magnetization, we think of it as processing around, and there's going to be a real and imaginary part to my magnetization. Okay, so the cosine lets me figure out the real part, and the sine lets me figure out the imaginary part. Okay, so I'm actually I'm converting this real signal and converting it into complex numbers. Okay, there'll typically be a low pass filter, which we'll talk about later, and then this thing is just what's called an analog to digital converter. And it does two things. One is it quantizes the signal such that it goes from an analog value to a digital number, but it also samples. Okay, so the sampling is what we care about. So we actually can think of something, it's sort of like sampling with some sample rate delta t. Okay, so we're taking a sample every delta t. All right.
What is the RF signal used for?
The radio frequency signal that's the MRI signal. So the RF signal is, let's say this is my object. It's got spins in it, and then I have a coil. Let's see, this is my coil. And then I put it into amplifier, so this is the RF signal. So the RF signal is the spins are processing at omega naught. And then we have a coil that's measuring that signal.
So you are just multiply cosine omega naught, you get the real part?
Yes. So imagine this is what's called quadrature detection. So basically, the way you can think about it is like, let's say there's a magnetization processing around like this, right? And it's going to give me this signal that's processing very quickly, right? Okay. But really, all I care about is sort of the phase of that signal, right? So to detect phase of a signal, I have to multiply by two things that are 90 degrees out of phase. That turns out to be a very effective way of doing it.
Okay. So, why just multiply? I think so. We got a RF signal, and then when we want to get the real part, we need to do the cosine to the RF signal.
Okay, so you're saying we have an RF signal, so that's just one number, right? So what would you do next with the RF signal?
So if we have an RF signal, like in the unit circle, something like this, so we do the cosine of the direction or the angle, so we got the real part.
Okay.
And then we do sine for the complex part.
For the imaginary part, yes.
Yeah.
Yeah, that's what this is doing. Yeah, so basically it's just sort of, the electronics is actually, these are what are called mixers. And you basically have two things that and the reference signal, they're just 90 degrees out of phase. Yeah. So if you want to, certainly that's a topic. If you want to delve into that more, that'd be a great project, looking at the signal processing, and we can certainly talk about that more offline if you want. It's especially if you're a DSP person, this is great. It's like you can really delve into this.
People want to learn more about the scientific.
Yes, certainly. Here's the thing. There's, depending on your background, like let's say you're a DSP person, there's a lot of cool DSP stuff you could do. If you're not a DSP person, then this is like, I don't want to do this. So then you would pick some other project. So just basically, that's where, if you have questions, ask them earlier, so you're not sort of making a decision at the last minute. Okay. And then just in practice, this isn't really how the processing is done. It's just giving a picture. And the main thing I want to emphasize here is we're getting a sample every delta t. So that's the sampling. Okay. So when we talk about how's the sampling being done, this is a sampling, and this is going to be related to delta kx. Right. So that's the first thing we're going to look at. So that's the sampling in kx. So basically, during this period here, while this gradient is on, we're going across k-space, right? We're moving across k-space. So the signal is coming in as we're zooming across k-space, okay? So as it's coming in, we're going to sample that signal. And we're going to sample that signal every delta t, okay? So that is shown by this ADC. It's going to acquire, it's essentially, it takes sort of the average signal every delta t and converts that to a digital number, right? And so let's look at the sampling. Well, if this has some gradient GXR, right, then the amount of area that it goes is the delta k. Okay, in a delta t, how much delta k do I accumulate? Well, that's just gamma over 2 pi times GXR times delta t is my area. Okay, so that gives me my delta kx. All right. So that means that if I've given my field of view, I can figure out my delta kx. And then the design problem comes, either I'm giving a delta t and I have to figure out GXR, or I'm given GXR and I have to figure out the delta t. And so typically, I think in the MATLAB, problems that I'll assign you to write some code on, will probably give you delta t and you have to figure out GXR. There'll be some variation of that. So it'll be fairly simple. You'll probably be given like field of view of x, delta t, and you have to come up with a function that figures out GXR subject to some constraints. Like, you can't have a gradient bigger than this, or you have to do something else, all right? So that's typically what these problems look like. So let's look through an example of that. So let's say you're given field of view is 25.6 centimeters and resolution is 0.1 centimeters or 1 millimeter, okay? And you have to design this readout gradient, all right? And you're just asked to design this GXR value. Okay. So the first thing you do is you can say, well, the field of view of x is just 1 over delta kx, right? And I know that's equal to gamma over 2 pi GXR delta t. And let's say you're given delta t equals 32 microseconds. Then you just plug in chug. You say, well, I'll solve for GXR. I plug in the FOV, I plug in gamma over 2 pi, and I plug in the delta t, and I go through it, and I end up with 0.28675 gauss per centimeter as my gradient. So that's this is like a variation of a calculation that's made in an MRI pulse sequence, okay? So any questions on that? So it's a fairly easy calculation. Okay, so now let's talk about resolution in the next direction. So we figured out the delta kx. Now we have to figure out how far out do I need to go in kx, right? That's my resolution. So remember, we're giving the resolution is 0.1 centimeters, right? So from that, we can solve directly for delta kx, right? We know delta kx is going to be 10 inverse centimeters, right? Okay. Now, what is delta kx? We also said that's 2 times kx max, right? Okay, so remember this readout gradient here from this point to this point is traversing all the way from here to here, right? It's going over the whole delta kx. So now we need to, so the area that's covered by this, that's my delta kx. That's my wkx. So this area is just gamma over 2 pi times GXR times tau sub x, okay? And that should equal wkx, right? Because that's the area that I cross, that gradient traverses. So let's apply that design. So delta kx we know is 1 over wkx, okay? And that sort of just corresponds to this formula. That's the formula we have. So now we had already solved for GXR here, right? We already know what GXR is here, right? So the FOV already determined that for us. Okay, so now we take that value of GX. So we have our delta x is 0.1 centimeters. So we know the delta x. Gamma over 2 pi is just given to us. Sorry, this should be Gauss. Okay, and then this is what we got previously. So we just plug and chug, and we end up with tau sub x equals 8.192 milliseconds. Okay, and it turns out that this is equal to n read over delta t, where n read is FOB of x over delta x is 256. I'm just saying that this is equals 256 times my, what was delta t again? 32 microseconds. Okay, so that's a sanity check you can do. For example, at least for these simple examples, I have, I know if I'm going across a field of view and I have some resolution, in my image is going to have 256 samples across it, right? And so to first order, it sort of makes sense that I have 256 samples in K-space to be able to, like, if I have 256 numbers in one domain, I probably need about 256 numbers in the other domain to be able to make that transition. Now, the answer is actually slightly more complicated because actually, since I have complex numbers, if I have 256 samples, I actually have 512 numbers, right? Because I have real and imaginary. Later on, we'll talk about there's this Hermitian symmetry where you don't actually need to acquire all of it, but we may or may not get to that. Okay, so let's do a simple problem in class. So because this is really what you'll be doing on the MATLAB is designing things. So you're asked to design a spin-warp readout gradient to achieve a field of view of 20 centimeters and a resolution of 2 millimeters. The maximum gradient strength available is 2 Gauss per centimeter, and the readout sampling period, this is your delta t, is 5 microseconds. What should be the amplitude, so that's the GXR of your readout gradient? Pick the closest answer, and you can use gamma over 2 pi equals 4,000 hertz per Gauss. Okay. So let's take maybe 4 minutes or so to do this. Just at least start the problem, and then we'll discuss how to do it when we reconvene. And I will open up the poll online so you can enter. We can do that. And feel free to talk to your neighbor too, or chat online. It's Okay, let's go ahead and in the next minute or so, go ahead and submit your best guess online, and then we'll take a poll in about a minute. Okay, so let's see what people think in class. So on the count of three, just say loudly as possible your favorite answers. So 1, 2, 3. Okay, there was like a very quiet beep from some brave soul. I don't know where. I don't look when you say it, so I'm not biasing myself. So um, if this was a democracy, we'd be doomed. So let's just hope that more of us vote than answer that question. Okay, so online, it's pretty equally split between B and C and F. So yeah, I don't expect you to get this in this short amount of time, but it's more just, if you at least think about it, then it's sort of, when we go over the question, then it sort of hopefully makes a little more sense. So here, the readout gradient looks like this, right? And we're asked to figure out this GXR. Okay. So we're given delta t is equal to 5 microseconds, right? So the GXR is really going to determine my delta kx, right? Right. So we know delta kx is equal to gamma over 2 pi times GXR times delta t, right? And we're not given delta t, and if we just knew delta kx, then we could solve for GXR, right? So what determines delta kx? Which parameter? Yeah. So everything else you can ignore, right? Right. So now we just solve, and it says closest answer because we may not get, the answer we get may not be doable, but we're just going to solve for it anyways, right? So we say GXR equals 1 over gamma over 2 pi field of view x over delta t, right? And we just see what we get. So let's do that. That's equal to 1 over 4,000 hertz per Gauss. Okay, field of view of x is what, 20 centimeters, right? And then we have 5 times 10 to the minus 6 seconds. Is that right? Okay. The hertz cancels out the seconds. And then the units here would be Gauss per centimeters, which is good, right? So we know we're going to get something in Gauss per centimeter. And now we just have to do some math, right? Whoops, sorry. So let's see, 20 times this is 100 times 10 to the minus, so these two together is 100 times 10 to the minus 6, which is 1 times 10 to the minus 4, right? And then 4,000 times that is, these two together are going to give me 4 times 10 to the 3, so 4 times 10 to the minus 1, right? So is that right? 0.4, right? So 1 over 0.4 is what, 2.5? Yeah. So actually, the required gradient is more than we can have. And this is one of the design issues you might end up with, is actually, hey, I need 2.5 Gauss per centimeter, but my machine can only give me 2 Gauss per centimeter. Okay, in which case, you're going to have to change something. You're either going to have to change your field of view, or you're going to have to change your delta t. Okay, so in this case, obviously the closest answer would be, F, right? But this is just pointing out two things. One is this is a fairly, just showing you these design problems are fairly straightforward, but also introducing you to the point that, hey, there might be some design constraints which might require you to change things. Okay. Typically, what that means on a scanner is you might enter something and it'll just come back and say, no, you can't do that. And it'll have some recommendations on what to do. Okay. The next thing we want to talk about is phase encode, the sampling in our delta in our ky. Okay, and remember what we do is we vary the amplitude of this from shot to shot. So we go out to one point in ky, and the next time we go out to another point. And so it's really the difference. So here where we had the black, it takes me here, and here it takes me here, right? So this difference here is my delta ky. Okay, so it's really the difference in the area between these two. My black, so my black has this amplitude and my blue has this amplitude. It's really the difference in those two areas that's going to give me my delta ky, right? Because that's the difference in how far I went out. Okay. So that incremental amplitude, we're going to call it GYI. So that's how much I increment the amplitude each time. And let's say I'm just given tau sub y. Okay. So I say my delta ky is gamma over 2 pi times that incremental amplitude times the length of time I have my gradient on for. And if I'm given FOV of y, then I can certainly solve for delta ky. And then I can solve for either GYI or tau y. All right. So let's look at an example of that. So let's say you're just given that tau y equals 4 milliseconds, 4.096 milliseconds. And then you just solve for GYI. So you're given, this is FOV. This, for some reason, I use this form of gamma over 2 pi. I don't know why. This negative sign should not be there. And then this was the tau sub y. And if I do all that, I end up with 0.00224 Gauss per centimeter. Okay, so that's, these typically tend to be fairly small numbers because we're just incrementing a little bit at a time. Now we have to talk about the resolution in the y direction. And so that's basically determined by the biggest gradient that I'm going to play out, right? Because that's going to be, this biggest gradient is going to determine how far out I go in ky. Okay. So I take my resolution and I can solve for WKY, and that's 2 times GY max, okay, or KY max. So I have gamma over 2 pi times 2 times GYP, where GYP is this maximum gradient I play out. Because in this case, I either play out a positive gradient or negative gradient, depending on where I am. And so I need to multiply that amplitude by 2 and then multiply by 2y. Right? So let's look at an example of that. So here, I just plug and chug in the formula. I solve for GYP, and I find it's 0.2868 Gauss per centimeters. And it turns out that that's equal to the number of phase encodes divided by 2 times GYI. So let's see whether that makes sense. So the number of phase encodes I'm saying is my FOV of y divided by my delta y. So how big my image is divided by the resolution. So saying we have 256 voxels in the y direction. Okay. So I probably need about 256 samples along KY, right? To have sort of same amount of information. And this is just saying that this amplitude here divided by these deltas, that's going to give me half those samples. Okay, so if I had 256, I'll about 128 here and 128 below. Now there's a question of asymmetry, because if you have 256 samples and you also go through 0, then you can't have, you have to have one less above or below, but talk about that later. Okay, so sorry, this is a really busy slide. I need to change this for next year or next time. But let's just go through this. I think, yeah. Let's see, what we have 10 minutes or 12 minutes left. So let me summarize this, and then we'll do one other problem together, and then we'll end for today. Okay, so let me just summarize here. So these are the sort of design problems you'll get. So you want to keep in mind that if you're given field of view of x, that really determines your delta kx. Okay, and delta kx for the readout depends on delta t and gxr. Okay, so that's where that comes in. The resolution affects how far out you go in k-space. And that's going to depend on both GXR, but also the total amount of time you acquire. Okay, so there's sort of things to keep in mind. On the phase encode side, the phase encode in the y direction determines your delta ky. That's going to be related to the length of this gradient and also the incremental amplitude GYI. Okay, and then how far you go out in k-space depends on this width, but also the biggest gradient you play out. All right. So let's actually, we're just gonna do one of these problems. So for now we're looking at a spin warp pulse sequence still. And now you're asked to design the phase encode gradient to achieve an FOV of 20 centimeters and a revolution of 2 millimeters. The maximum gradient strength available is 6 Gauss per centimeter. What is the minimum width you can use for your pulse, for those little gradient pulses? Okay, so this is slightly different design problem. So go ahead and think about that, and when we regroup, we'll talk about that. Okay, about another minute, and then just put in your best guess. Okay, so let's sort of poll in class. So just at the count of 3, just sort of say as loud as you can what you think is the most likely answer. Okay, ready? 1, 2, 3. Okay, C and D. Online, the C gets the most votes at 70%, D and E 21 and 14% each. So it seems like people are basically, it's very good test taking skills. You want to pick sort of the middle answer and don't go to the extremes, but let's see which one it is, okay? All right. So let's think about this, right? Remember the phase encode gradients are these sort of things where we vary the amplitude, right? And these in K space, what they're meant to do is get us out to some point like that, right? And the maximum we want to go is some WKY, right? And so we're limited in the maximum gradient strength we have, 6 Gauss per centimeters, right? So that means that that's going to really put a limit on how fast we can get out to one of these endpoints, right? That's the main constraint. It's not really going to constrain how much these little steps we take. It's probably not going to constrain that too much. So it's really how far I can get out, way out to there or way out to there. All right. So the main thing that tends to say that what I really care about is the resolution. Okay. So in this case, delta y is equal to 0.2 centimeters. Okay. So that means WKY is equal to 5 inverse centimeters. Okay. And what is delta ky? Well, if the maximum I can go is -6 in either direction, right? Okay. Then this whole area here, right? The maximum I can go swinging from the most negative to the most positive, that will traverse 12 Gauss per centimeter times the time I have that I play it out, this tau sub y. Okay. That's the maximum. That's if I have to go from the most negative to the most positive, that's the maximum I can do to go from here to here, which is my WKY. Okay. So we know that's equal to gamma over 2 pi times 12 Gauss per centimeter times the time. So now we just solve for the time. All right. So let's try that. Tau sub y equals 5 inverse centimeters. We have 4,000 here and 12 here, right? So let's see how that works out. This is 12 Gauss per centimeter, hertz per Gauss. Let's see if this works out. So, so I'm going to end up with, let's look at the unit. Centimeters inverse, right? I have Gauss over hertz, and I have centimeters over Gauss. So these cancel out, and 1 over hertz is seconds. So that's good. At least the formula is correct. Okay. So checking the units is always good. So now I have confidence that if I go through the trouble of figuring this out, at least the units will be correct. So basically I have 5 over, what is that? 48,000, right? Is that right? 48 times 10 to the 3, is that right? Which equals 5 over 5 times 10 to the, what is that, 4, right? It is approximately equal to about 5 times 10 to the 4, right? Which is approximately 1 times 10 to the minus 4 seconds, which is equal to 100 microseconds. Okay, so everyone okay with that? So as you can sort of see, the algebra for all this is pretty simple. The calculations and the stuff you do in your MATLAB code, it's not going to be very complicated algebra or anything like that. But it is going to be, you have to make sure you're sort of thinking about, oh, if I hit this constraint, what do I do? How do I change things? Okay. So for those of you who came in late or joining us late, go back to the beginning of the recorded lecture here. I do go into depth about sort of what the MATLAB, what the assignments will look like, and I'll also send out an announcement later today, just giving people a heads up. The bottom line is there'll be 1 more homework assignment. You have 2 weeks, approximately 2 weeks to do it, but I'll be sort of probably rolling out chunks over the next few days as I figure out how to use the MATLAB grader and come up with problems. Okay. And if you have questions, let me know. I do want to encourage people to, as you see them, just at least try them so I get feedback and we can debug it early in the process. So just for those problems and also everything here, we've assumed ideal gradients that are just rectangular. And so for most of the problems, unless you're told otherwise, you can assume rectangular gradients. I do want to end saying in the real world, we can't do that. Okay, in the real world, we always end up with something that's more trapezoidal because it takes time to ramp things up and ramp things down. I was thinking of doing a problem like that. I'm maybe probably won't because I'm not sure it's the most important thing to cover, but just realize if you go out and do an MRI in the real world, you will see a lot of trapezoidal gradients, or in the old days, even sinusoidal gradients. Okay, so with that, we're going to end today's lecture. So we'll see you all next week. If you have questions, feel free to either ask me here or online. And that will end today's lecture.